not letting me. Um,
Yeah, I think
this
it's
meeting is being recorded by the host or a participant. I got it. All right, good. So, Anmol, let me know if you have there is a way to upload the recording. Let me know about it, and then I'll help you.
okay.
I don't understand why it wouldn't do it. I have old software on this computer.
Mhm.
All right, so let me start my share screen. What I want to do is I actually want to open up. Actually, what I really want to do is I want to start Jupyter Notebook. So hang on, let me see if I got that going. Um, and then we'll go from here. I think it's launching. Again, I'm using a super old computer, and I gotta hope that it's launching. And the answer is it sure doesn't look like it's launching, but it will. You guys give me a break. Okay, something's happening. All right, I'm going to share my screen now, and then we'll go from there. Yeah, I'm going to share my desktop. Let's hope that I don't have anything bad on my desktop for you. Okay. So, you should be seeing my desktop right now. Do you see a screen that shows? Can you guys see a screen that shows a list of Jupyter notebooks starting? So yeah,
Yeah,
so
we
you can
can.
see it, right? All right. So let's start off by going to classes. This is where we were last time. And then I want to show you about how to do kernel estimation for your homework that's due on Thursday, and then even talk about why we would do it. So where we were last time was the end of the second week. Um, I am very confused, baby. All right, end of the second week. Um, here I was. Oh, I can't even believe it. You know what I have right here? This this thing thinks that I am in so old. I have to. It doesn't even. It doesn't even have the. It thinks it's a spring quarter of 2023. So you see that? No wonder I'm having a problem here. And so this computer is so old that it hasn't been turned on since a year ago, and the date is even wrong. So hang on, guys. That kind of makes sense about why it wasn't doing anything. All right, here it says winter quarter. Here it says canvas for you guys. Here it says Quanticon, very good. All right, so where we were was I was talking about the multiplier accelerator model. That's where we're going to go. And then also I wanted to show you kernel density estimator. So I was right here, and I'm going to download AR1 processes, and then I want to open it. And I cannot. So where is my? Okay, finally. This took forever. Sorry, guys. 9:30. But all right. So we were going about AR1 processes. I was saying to you, hey, here was convergence. This was showing what a convergence and distribution meant. And then I was talking about what does ergodic mean. So what this thing is showing you is it's showing you a bunch of pictures of a normal variable whose mean and variance is converging to the long run mean and variance of the AR1 process. You remember how we can figure out what the mean and variance were? That's just by using the difference notation. And in particular, if there's an AR1 process, for example, xt equals 0.9 times xt minus 1 plus a normal random 0, 1 variable, then its mean is going to be 0 divided by 1 minus 0.9, so that's going to be 0, and its variance is going to be the variance of the normal 0, 1, which is 1, divided by 1 minus 0.9 squared, and that's what this is showing you. Now, you may want to know, when are you interested in estimating, this does happen, a whole density function. So what I'm showing you right now is the following idea. Say I gave you several observations of a random process. And so that on this, so you should open up to the notebook exercise, AR1 processes. Look at exercise 24.2 from Sargent. All right, what is this thing? Xi is the realization of the ith variable. And so if I could draw it on a blackboard, what you would see is I have a bunch of random points that have come up. And I don't know what distribution is it drawn from. So there is a technique of not estimating mean or estimating the variance. So say I told you, I'm going to ask Doris now. I got 3 xi's. I got 2, I got 7, and I got 5. Those are your 3 random realizations. So I'm going to say, Doris, what's the distribution that comes from? 2, 7, and 5. What would you do? How would you even think about it? Could you estimate the mean, for example? You certainly know how to do the sample mean, add them up and divide by 3. Could you estimate the variance? Yeah, you have 3 points, so you have an estimate of the mean, and then you get squared deviations from the mean, and then divide by the sample size minus 1, and you have an unbiased estimator of the variance. But who's telling you that it's a normal distribution? Who's telling you anything about it? You don't know what the shape of it is. So what would you do? You have these numbers, 2, 5, and 7. So sometimes you want to be able to estimate the whole density function. So does everybody get the idea of what I want to do? Now let's look at this thing. This f of x is the probability density function that you could estimate. And how would you do it? You start out with a k. K is a guess. It's called the kernel. It is the building block density that you're going to use in your estimation process. So k is a function of x, and you look at the deviations of little x from the realization you had. So the first realization we had in my example was 2. Now, h is how wide you're sampling around 2. Notice x can be bigger than 2, x can be less than 2, because it's a variable. I'm looking at little x here. How many realizations do you have? 3. So I'm going to do from 1 to 3. And one of the big xi's will be 2, the other will be 5, the other will be 7. And I'm going to say, okay, I'm going to assume that there's this kernel that I know. And we'll talk about what are normal kernels that you would use. And I'll use it as a building block to do such an estimation. So everybody understand where I'm going? A little bit, the idea. Why do I want to do an estimation? So anyway, let me start this notebook. Let me just start running the stuff. Well, actually, I've run enough so that I could show you here. All right. So remember this formula and get a handle on it. Now the h I'm going to come back to in a little while. Before I proceed, let me ask you this. If I have 2 density functions, one is a normal 0, 1, and the other is a normal 10 with mean normal with mean 10, variance 7. And I add up those 2 density functions. Do I get another density function? So it would literally be adding 2 bell-shaped curves. Do I end up getting another density function? So who wants to try? I see somebody in the chat. Oh, is this the idea behind Bayesian stats? Nope, but it's going to give you an introduction to it. But it's a deeper idea. It's like Anmol, you guys should just start talking, because I can't see very well because of the old computer. All right, so what Morgan said is, hey, if I have 2 distributions added together, does that give me a chi-squared? And so the answer to Morgan's question is, if I take a normal random variable and square it up, and I take another normal random variable and square it up, and then I look at the distribution of 2 normal random variables squared up, what do I get? That does define a chi-squared random variable with 2 degrees of freedom. But I'm actually asking you this, what I could do. So draw a picture on the blackboard. I'm going to stop my screen share, and I want somebody who can. Does anybody have a whiteboard that you can actually draw on? Okay. Who? All right. So who's drawing for me? Who's my all right. So Dorji, Dorj, draw a normal variable. Just draw it on the x-axis, and then draw a probability distribution function on the y-axis.
Okay.
It's kind of weird. I'm seeing everybody's name.
Yep. I don't
If you
know
can't
how
do
to
it, it's okay.
draw on it. Yeah.
All right,
Okay.
good.
So yeah, everybody's in it. So
All right, and I see something. I see like a drawing tool. Could you get rid of that if it's possible? All right, so look what George is trying to do. George is trying to add one. So what do you know about any probability density function? The area under the curve has to be what? First of all, it's got to be all positive numbers. It has to be 1. So, and then if I add another curve on top of it, and I integrate up to 2 when I'm adding one and the other one, what's it going to integrate up to? 2, because I'm adding 2 together. So you see, that's not okay. But if I take 50% of one and 50% of the other, and then I integrate that up, I'm going to get half of, when I integrate it, half of 1 plus another half of 1. And when I integrate that up, that's going to be 1. Or a 30/70, when I integrate it up, it's going to be 1. So the key idea for any density function is a convex combination, 20/80, 50/50, 70/30 of 2 density functions is another density function. Why? Because I'm adding up all positive numbers, and the integration, it maintains regularity in adding. Integration is additive. So adding 2 together, as long as I scale them appropriately, gives me another density function. Okay, so George, can you stop the share? All right, so let's go back and let's look at I'm going to try again, share screen, see if I can do it better now. Somehow I can't get this thing to work appropriately. Hang on. I can only share my desktop. I'm sorry about that. This thing's a little bit crazy. It's not so easy for me to show everything, and I sure hope I don't have bad things on my desktop. All right. So you see this formula here. What's it doing? It's adding up n. So for right now, make H1. So it's adding, and K is a little density. So it's adding up K different densities. But, excuse me, it's adding up N different densities. But then it's dividing, it's multiplying times 1 over N, or it's dividing by N. So this thing is a density function when H is 1. Now, what could be a kernel that's normally used? The normally you could use a normal density, you could use a uniform density, or you could use something that has a funny name called a Pachenikov kernel. That's an optimal one. But it's anything that's a density centered around the observation x sub I. So now, what is this H? H is saying how wide out you sample around the observation big X sub I. And if it's out H, this is like a change of scale of the variable. Then in order to keep it a density, you have to divide by H outside the density because you've done a change of variables. So this formula just says in your computer, you have a sample of N observations. I had 3, 2, 5, and 7. I pick a bandwidth. So maybe my bandwidth is 10. So then I use a density that is normal for this operation. And I'm telling you, either it's a normal random variable, or it's uniform, or it's something that's a tent-shaped density. And then I add them up, and that's how I get my density. So let's take a look. I'm gonna run and restart this whole thing. Hope this thing works, and then I can do it interactively. So and then what you should do for doing your homework on Thursday is you should look up kernel density estimation in ChatGPT. Okay, so it worked. All right, now, so let's see. Very good, very good. Did it go? Yeah. All right, so here's a solution to exercise 24.2 that I gave, and all right, the uniform distribution is not defined. All right, so that's my bug. So who knows what I did to unbug this thing? What should I do? So I'm going to have to import uniform from my I'm going to have to import uniform from the stats package because it doesn't know what a uniform density is. So how would I do it? So I would just plug in ChatGPT right here. Oh man, I feel terrible that I cannot use. I feel terrible because I don't have a mouse and I'm not good with the trackpad on the old Mac. Yeah, thanks a lot. You have it, Morgan?
Yeah. It's from
It's got to be from.
Skippy.stats important.
Yeah. So what do you
From SCIPY.stats.
Yeah. Okay.
SciPy.stats.
Okay.
Import uniform.
Okay. So let's go back to where we were, the AR1 processes. Again, I feel terrible. I'm going to have to go up and get a mouse. So what I need to do is solution to exercise 1 here. I need from skippy.stats import uniform. All right, so remember what the uniform distribution does. It's flat and it's centered from 0 to 1. So I'm actually gonna, and so the way that it works, so let me run this thing again. Let's see if that worked, that went through. Yeah, so all right, now, the command that I'm using is I'm saying the kernel density K is uniform. It starts at -1 and it goes out 2. So in your mind, imagine a flat line that starts at -1, goes across 0, and goes out to +1. So its width is 2. So if that's a distribution and it's flat, its height must be 1/2. So that's the thing that I'm looking at. And I'm using that because that is a probability dense distribution. So let me ask you, with that probability distribution, what's the probability that I see a random variable between 7 and 7.2? Remember, it starts at -1 and it goes out to 1 and it's flat on either side.
0. I don't think you could see that.
So it's 0. So that's what the bandwidth means. It's only sampling around from -1 to +1, centered on the observation. So remember, in the example I was talking about was 2, 5, and 7. So it would take the first one, it would center it on 2, and it would go from 1 below 2 to 1 above 2. And it's very well behaved. I like a flat distribution because in my brain, I can handle that. So everybody gets that idea. So now what I'm going to do is this is a class that Sargent and Stachersky wrote for you. Let's execute the next cell. Hope it works. So again, it's defining a plotter. Now, what I'm gonna do is, let me, instead of having so first I'll show you what it does, and then we're gonna play with this next cell a bunch of times to show you what I'm expecting for your Thursday homework. So I'll just do this one right now. All right, so look what happened. It's plotting the true density, and what it's taking is, where's my alpha and where's my beta? I must have defined them somewhere. Do you guys see for alpha, beta, and pairs? Yeah. So I'm doing several different alphas and betas. So parameter pairs are 0.5, 0 and 1, and 1 and 1. So I'm gonna try to estimate 3 different normal random 0, 1 variables. All right, not 3 different normal variables. One is centered at 0 and its variance, its standard deviation is 0.5 or variance, I forget the parameters, and then 0, 1, and then 1, 1. And now, look, the true distribution is the pumpkin colored line, and the thing that I estimated is this little blue thing. So let's imagine, instead of having, and then I got it for all 3 situations. So let's imagine, instead of just having 5,000 sample, let's imagine I only had 5 random variables. All right, so what I'm gonna do is now look what happened. If I only had 5 variables, what are my estimated, what's happening? Look at the blue lines. What are those blue things? What is it telling you? So anybody want to give a guess what I'm showing? Look at the blue lines. You should do it. What's it guessing? Where did it come up with these numbers? Anybody have an idea? Morgan, you want to guess?
From that function.
Yeah, because remember, the kernel density is a bunch of flat lines, right? So it's taking 5 numbers. Oh, it just got dark in here. It's taken 5 numbers and it's guessing, oh, this is my best guess for the density that we're looking at. And it's not a very good estimation. But is it a density? Yes. Now we're starting off with these normal variables. What would happen if instead of having 5 observations, I had around 10? So I have 10 observations from a normal variable, and this is, I'm using 3 different examples here. I'm going to run it again with 10. Am I starting to get a better estimate of a density? Yep. Now, let me ask you, because I see Caleb. Caleb's like a handsome guy, and he's the only guy I see right in my, of all the guys. So Caleb, what's the use of estimating a whole density? Why would you even want a density?
Well, if you can, a lot of our models kind of depend on having the density, right? Because a lot of our models are like MLE requires us to have the density. Another reason you can want the density is it tells you the mean and standard deviation, like what are the possible values, the likely values for your variable or what you're estimating.
Okay, so I like that. But even when you do maximum likelihood estimation with Kuhn, you usually say, oh, I assume that the distribution is normally distributed, or I assume you have to come up with a distribution. But if I gave you, if we just look at the 10 numbers, so at this point now, I'm going to show you your homework that's coming up for this week. So your homework coming up for this week is going to look like this. So let's go here. Whoops, not there. Don't need that. And then I need some help from you guys about how to grade your homework, because I should have done it already, but I don't know how to do it. All right. So if I'm over here, and I look at the assignments, look at assignment that you have to do for Thursday. All right, so I gave you some data right here. These are the weights of the students from last year's class in pounds. All right, so can everybody click on assignment number 2 and just take a look at it right now? All right, so George or Caleb or anybody or Hunter, read the first few observations. You have like 25
182.
numbers right
Yeah.
Yeah, 182, 127, 117, 187, 110. Does that look normal to you?
Like
Kind of
normally
hard to
distributed, or
visualize.
Yeah,
Yes.
does that look normal? All right, so if you look at it closely enough, it's bimodal. There's people with big body mass and people with small body mass. So if you drew the distribution, it wouldn't look at all like a normal variable, because normal has one mode right in the center near the mean. So the data speak for themselves, but I could ask you, what's the probability that somebody in this class weighs 135 pounds or less? I could ask you that. And if you had the density, you could say, oh, I got it, because I know an estimate for the density. 135 is my cutoff. I integrate from the bottom of the density up to 135. That will give me a probability, the answer to Fisher's question. If I had the density, I could say to you, what's the variance of these weights? And you would say, oh, Fisher, I have the density. I know what the mean is from the density. Then I can do X minus the mean. I can square it up and I can integrate numerically with the density and I can get the variance. But you would say, Fisher, variance here is tricky because it's not a unimodal distribution. So what you would do when you have to do this homework is take a look at it, plot it using a histogram, and you're going to see there's a bunch of people who weigh around 120 and a bunch of people who weigh around 180. Now, why is that? Why does that make sense?
Gender
I
specific.
mean, remember, I have over here Morgan sitting right next to me, right?
Yeah.
And he's a big guy with big body mass. I'm not going to punch his face in, right? Because I'll be dead in 1 second, right? So what is this really describing?
2 different means.
It's describing men and women. Men have big body mass, or some people have big body mass, and other people have small body mass. So the distribution itself is very interesting. So that's what you're going to do. When you run this, when you do this, then I'm going to ask you to estimate the distribution from which the student weights were drawn. So can you see where I'm going? And now I'm going to go to Amal's question. Amal, you're there, my man? So
Yes.
turn on Amal. All right. So are you in your PJs? No, you're okay. All right. So so is this Bayesian or is this like more general than Bayesian? You're muted, buddy.
More general, kind of using the idea behind it, but definitely just broad.
All right. So does it make sense to you that you should know something about how to estimate a whole density function, the whole thing? Does that make sense to you?
Mm-hmm.
So here's Nicholas is asking this question. Why is it better to assume a distribution for MLE rather than estimate one? So this is a huge, big question. Good question. Excellent question. Now, when you assume something's normally distributed, what gives you a complete description of the whole distribution? 2 moments: the mean and the variance. So if I assume that Amal is a human being, can I go really far with my inference about Amal, right? But maybe Amal's a very, very clever cyborg, or maybe he comes from Venus. But my assumption of him being a human being gets me a lot of analytical traction when I do statistical inference about him, right? However, your conclusions are only as good as your assumptions. So another way of asking Nicholas's question would be, when is it okay to assume that doing maximum likelihood estimation, everything's normally distributed? Well, in some cases it is, some cases it's not. Let me give you some classic data in, all right, so for financial data, for changes in the stock market from day to day, who knows anything about that? Because the stock market just hit a record high on Friday, and it was pretty close, a little bit high, it closed a little high yesterday, even on Monday. So changes from day to day on the stock market, are they normally distributed with a little bit of an uptick on average? Who knows the answer? You should know this a little bit for any job interviews you guys have. Let me ask you, Gavin, you know anything about the stock market? Changes from day to day? What about the stock market?
You still get T distribution, right, sir?
Say again, Doris, or say Gavin, what were you saying?
All right, Gavin, you were saying something?
No, go ahead, George.
All right, it should be like, it should look like a T distribution, right? As it held.
Yeah, so where Doris, your computer doesn't have good bandwidth. It's processing slowly, so I hear your words with distortion. But I think Doris said it's thick-tailed. It's not the same as the normal. The normal comes down rather quickly in the tails. But stock market distribution, you have some really big days and some terrible days that changes, and therefore it's not properly distributed by a normal distribution. Now, what would be the practical if you're doing maximum likelihood estimation? Again, I'm still answering Nicholas's question. What would be the practical implications if you assume it's normal, and then you estimate and you go to your boss and say, here's the mean and standard deviation of changes in the stock market?
You undervalue.
How could you make your company go bankrupt? What could you be doing wrong?
You undervalue the extremes, so you kind of have, like, I guess, a moral hazard issue there.
Yeah. So what most companies want is they want extreme tail risk. They call it the 5% tail risk. So you're supposed to be able to say, I am 95% sure that this is the worst thing that can ever happen. And then that means you're telling to the company 5% chance you're going to go bankrupt. But if you're assuming a normal distribution and it's a thick tail distribution, you're going to be way off. And that could be catastrophic. All right. So do you see? So where's Nicholas, who was asking the question? Raise your hand, because I don't know who Nicholas is. It was a really good question. Oh yeah, Nicholas, you're down there, right? Say hi to me, will you?
What's up?
All right. So did I answer your question about what the advantages and disadvantages of making assumptions on distributions?
Right. So with the stock market, you're saying it would be better to estimate the density rather than assume a normal, right? If I'm understanding.
Yeah, no, but in anything, when you make an assumption about anything, if it's a good assumption, it gets you mileage. If it's a bad assumption, then as smart as you are and do everything right on your homework, you're going to get a wrong conclusion because you started with wrong assumptions. That's the basic idea. So now I'm trying to say to you, what economic data are not normal? All right, so who knows another? So what about the distribution of wealth in the world? What does that look like? Almost everybody has between $0 and $10,000. Almost everybody in the world is poor, like 3 billion people. Then, does anybody have negative wealth? Hardly anybody, because that means you're in debt or prison. All right, but all right, but then as you go more and more out towards billions and billions of dollars, it's not normally distributed. It's actually called a Pareto distribution. It has a long right tail. Same thing with rainfall in San Luis Obispo County. Rainfall in San Luis Obispo County it has a mode of around 14 inches per year and a long right tail where sometimes there's 40 or 60 inches of rain in some years. So if you know that the distribution has unusual properties, it's a really good idea to do kernel estimation to see what the distribution looks like. So at the very minimum, plot the histogram that's gonna give you an estimate of a distribution. Okay? Does that make a little bit of sense?
How
So
much
when I'm,
data is usually good to have to do this estimation? Like how many observations do you need?
so the answer to that is I don't know, and it's really cool that if you do it with around 20 or 30 observations, you're gonna get a smooth density function. But another way to ask Nicholas's question was, all right, what is the correct bandwidth? And if we go back and we look at the bandwidth says, how do you center around the observations? And so the bandwidth, there's a formula, and it's given in the Wikipedia entry for kernel estimation that says go this wide if you have this many observations. So you want to sample finely enough so that you're connecting a bunch of lines that make sense. But all right, so I'm going to answer as a rough rule of thumb, 20 or 30 is okay. 5,000 is overkill. What I want to do now is I want to pause the recording and give you guys a break. And I want to see, can we come back and